Hi, Daniel. How are you tonight? Can you hear me?
Yeah.
Oh, okay. I wasn't sure. Okay, so we into calculus yet?
Sorry, I'm running out of state right now. I'm not quite organized.
Okay.
Well,
You started limits?
no, not yet.
Okay. We're not into calculus yet then.
Okay. I'll be right back. I need to grab my book.
Okay.
I got it.
Okay. And either sequences, series, probability, statistics, or conic sections, I guess.
Like, with polar equation.
Okay, polar equations.
Okay, so this one calculates that from equation, the rectangular form, and the graph.
Okay, what's the equation?
The first one is -2 cosecant theta.
Equals what?
R equals -2 cosecant theta. Sorry.
Okay. When we're talking polar versus rectangular, there's three very important equations that you need to use to switch. First of all, you have x squared plus y squared equals r squared. You have x. Here, let me tell you how you can figure this out. Here's a polar equation. What is the cosine of theta equal to?
That would be x over r.
Which means x equals r cosine of theta. What's the sine of theta equal to?
Y over r.
Which means y equals r sine theta. So you need to memorize those, but you can always figure them out. Remember that we're going to graph polar and rectangular on the same grid. They're not different grids. They're the same grid. And x squared plus y squared equals r squared, because that's a right triangle. Okay? So, first of all, let's get this in terms of sine or cosine, so we can apply these formulas. So if r equals -2 cosecant of theta, what is it in terms of sine?
Would just be 1 over sine theta, or is that
Like that. Now multiply both sides by sine theta. And that is equal to y. So the rectangular equation is that. Okay? And that's the way we're going to do all of these, is we're going to use these three equations to convert from polar to rectangular or vice versa. Next.
Next one.
Some of them require a little bit more than just that, but we'll address that when we get to it.
R cosine theta equals 1.
Okay. Well, this is the same as R over sine theta equals 1. Well, let's multiply both sides by sine theta, so we get R equals sine theta. R
Could we do R squared equals R sine theta?
Yeah, that's the thing you have to do sometimes, is to multiply both sides by R. Now, R squared is x squared plus y squared, and R sine theta is y. So there's our rectangular equation. And the biggest thing we had to think of is to multiply both sides by R. That's the trick with a lot of these. And it's not obvious. I'm not sure, if I didn't know that technique, whether I would immediately think of it, but that's frequently what you have to do. I think that's about the most sophisticated thing you have to do to convert some of these polars back to rectangular. What else?
Next is convert the rectangular equation to polar form.
Okay.
The first one, oh, sorry, no, I skipped one. Okay, so the rectangular to polar.
Okay.
Or polar to rectangular.
Polar to rectangular, okay.
R equals 4 cosine theta minus 4 sine theta.
Think in a second. Let's see, what should we do here? We could square both sides. Squaring both sides is going to give us a nice advantage, I think. Because one thing, we're going to end up with a cosine squared plus a sine squared, which we'll be able to turn into 1. And the other thing is we're going to end up with r squared, which will turn into x squared plus y squared. So let's try that. Let's square both sides. Excuse me. Let's multiply both sides by r, not square. Okay? So if I multiply the left by r, I get that. Multiply the right by r, I get this. And now I can directly substitute from my two equations. R squared is x squared plus y squared. 4r cosine theta is 4x. 4r sine theta is 4y. You could put these in standard format. I don't know if they want it in standard format or that what I have circled there is sufficient.
Doesn't say.
Should be sufficient then. As long as we can get rid of all the thetas and the r's and end up with nothing but x's and y's, we've done our job. So again, the secret was to multiply both sides by r. That's as hard as I've seen, actually. I haven't seen a technique other than having to multiply both sides by r that's any more sophisticated than that. But that's a good thing to remember. I almost didn't there. I was going to square both sides instead of multiply both by r. Okay, now we're going rectangular to polar. What's the first rectangular one?
2x minus 3y equals 5.
These are a little easier in that they don't really require any kind of creative manipulation. Just substitute for x, substitute for y, and you're there almost. Let's see. If we have 2r cosine theta minus 3r sine theta equals 5, well, there's the polar equation. They probably want it solved for r, so let's factor an r out and then divide by the remaining coefficients, which is going to be 2 cosine theta minus 3 sine theta. In other words, if you have to have r on one side all by itself, that's how we can get it over there. Okay. Let me move that over a little bit so I have a little more room.
Okay, next is x squared plus parenthesis y minus 1 and parenthesis squared
Equals 1?
Yeah.
Okay. What's that the equation of? Circle.
Oh, yeah.
Okay. So we're going to find out what the equivalent polar equation of a circle is. And you're going to realize why polar coordinates are so valuable. That's a complicated equation. Well, let's make it less complicated. What can I replace x squared and y squared with? Or x squared plus y squared?
R squared.
Y is r sine of theta. And the ones cancel. Factor out an r. Ooh. No, this is right. R times r minus 2 sine theta equals 0. Let's not factor out an r. Let's move this to the other side, where we have r squared equals 2r sine theta. And then if we, in other words, remember the step where we multiplied both sides by r? Well, now we're going to divide both sides by r. That's the equation of a circle in polar. Much more straightforward than this up here. Now, technically, I shouldn't really be allowed to divide both sides by r, because if r is 0, you lose that solution when you do that. but r is never 0 in a polar. And I suppose the origin r is 0, but let's ignore that for the moment. Oh, I see the other way we would do this. Yeah. Well, let me go back and do it the way I was going to do it. The proper algebraic way here is not to divide both sides by r. The proper algebraic way is to do this. That tells me that either r equals 0 or this part equals 0, which means r equals 2 sine theta. So there's actually two polar equations that work. R equals 0, r equals 2 sine theta. But this is the one I'm sure they're looking for, probably the only one. Okay, let me get rid of those three things so you see if you got them memorized. Don't have them sitting in front of you either.
Okay.
In other words, a common mistake that an awful lot of my students make is they'll write these formulas, they'll either have the book open or they'll have it on a piece of paper, and every time they go to use it, they look at it. And you can do that for 3 weeks and never memorize it, because your brain just isn't going to memorize it if it's always looking it up. So when you're trying to memorize this stuff, it's good to put it aside and see if you've got it memorized. And if you don't, try to memorize it again and do the same exercise. But the point is that don't have it sitting in front of you. Once you have it memorized, it'll reinforce much better if you don't have it in front of you. So what's the next rectangular one?
Next is x minus 1 squared.
X minus 11
1.
plus 11 squared?
No, x minus 1 squared. Yeah.
Sorry.
Plus x plus 4 squared.
Plus y plus 4 squared?
Or, yeah, y plus 4 squared, sorry. Equals 17.
Another circle. Well, let's do what we did last time. Expand each of these formulae.
Okay.
You want to get so you can do these without having to FOIL them. In other words, you want to know what a minus b squared is. It's a squared minus 2ab plus b squared. Okay? If you have these memorized, then you can do little exercises like this much quicker than if you have to actually FOIL it each time. So what's this one?
Let's see, x squared minus 2x. Yeah, minus.
Plus 1.
Oh, okay.
Okay? And the other one?
Y squared plus 2y.
It's right. It's this times 2. Okay. Now the x squared plus y squared, I can substitute. I can substitute for x in terms of theta, and I can substitute for y in terms of theta. So let's do all of our substitutions, and then we'll organize everything and solve for r.
Okay. It will be r squared minus 2r cosine
let's get rid of that 1, that's 16, and that's 17 also.
Okay.
And we've now taken care of that, and that.
Plus 8 sine theta, or 8 r sine theta.
Now once it, okay, so that's all equal to 0. What's the next step?
Now we get r by itself. So do you factor r out last time?
Yeah, we can do it that way, although it actually makes more sense to just always assume r is never going to be 0. So let's go ahead and move these to the right side of the equation and then divide both sides by r.
Okay.
And that's going to give us what?
Equals, r equals 2 cosine theta minus 8 sine theta.
That's just the quickest way to do it. We'll violate that one rule where you can't divide by a variable that might be 0. And we're going to violate it because we're going to assume r is not 0. Even though you can see that that is a solution. R can be 0. Everything would be 0, and this equation would be valid if r is 0. But that's not a helpful polar equation, so this is the other part of it that we would get if we did factor the r out and solve for both of them. Okay, what else you got?
Okay, this one, it says the location given in polar coordinates of 2 planes approaching an airport are 4 miles 12 degrees and 2 miles 72 degrees. Find the distance between the airplanes.
Do they measure everything from the north? Did they say the bearing of these planes? I don't think it matters, actually. We're going to do it from the x-axis.
Yeah, I think it should be from that x-axis.
Okay, so the first polar thing, that's 4, that's 12 degrees. The next polar thing is, in other words, we're looking at vectors. And that entire angle is 72 degrees. Well, this plane ends up there. This plane ends up there, so we need to solve for that side of that triangle. Well, let's draw the triangle outside the grid here so we can see what we're looking at. What's this angle right here?
Not sure.
60. The difference between 72 and 12.
Okay.
This side is still 2, and this side is still 4. How do we solve that triangle to solve for x?
We would have to do the law of cosines.
Yep. So, law of cosines, x squared equals what?
I can't remember.
Think of it as the Pythagorean theorem with extra stuff. Pythagorean theorem would be 2 squared plus 4 squared. But then we have to subtract off what? What goes here and here?
That'd be...
Those two sides, 2 and 4.
Oh, okay.
Okay? So x equals the square root of 20 minus 16 cosine of 60 degrees is 1/2. So x would equal the square root of 12, which is 2 root 3. That's the distance between the two planes. I'm sorry? Yes, it would be miles. Because the planes are going 4 miles and 2 miles. So that's going to be in miles.
Okay.
And I say it didn't matter whether our bearing was from the north or from the x-axis. It's still going to create that specific triangle where that angle is going to be 60 degrees regardless of how we, in other words, if it's 12 degrees from north, the triangle is going to look a little different, but it's still going to basically be that triangle.
Okay. Well, I think with polar coordinates, it normally is the x-axis.
It is, yeah. But with bearings of airplanes, it's normally from the north. In other words, if you say a plane is going at 400 miles per hour, the bearing of 12 degrees, they mean 12 degrees from the north. There's your 12 degrees right there. But you're right, in polar it's always measured counterclockwise from the x-axis.
Next one is a regular pentagon whose center is at the origin, has one vertex on the positive x-axis at a distance of a from the center. Find polar coordinates of the vertices.
Wow. This is a regular pentagon.
Yeah.
I can't even draw it like that, can I?
I don't think so.
No, let's see. Something like that.
Yeah.
Okay. And what did it say that it has? These are the vertices on the x-axis?
The center is at the origin, and it has one vertex on the positive x-axis at a distance a.
Okay. So I can say that's a vertex right there. Let's get rid of this. Let's try to draw it. So if I make that the vertex,
My teacher said that I think I remember correctly, he said that none of the other points would fall on an axis. So
none of the other vertices would fall on an axis?
yeah.
Which is not the way I've drawn it, is it?
Yeah.
All right.
If I remember correctly, it may.
Well, certainly these two don't. And how the heck are we going to determine these vertices anyway? Well, let's examine this thing up here. If indeed this distance is a, What is this distance?
Those would also be A.
Every one of them. So, if the center is there, that has to be A also. That has to be minus A. In other words, this would be A comma 0. This would be 0 comma A. This would be minus A comma 0. Now we got to figure out what that one is. Well, if I know that that's A, I know this angle. Don't I know that angle? What's each one of these central angles? Well, what's the total? There's 360. There's how many of these angles?
5.
So that makes the central angle 72 degrees, which makes this angle 36 degrees. So now I have a triangle whose hypotenuse is A and has an angle of 36 degrees. That's going to allow us to figure out the coordinates of this point right there. What trig function can I use? What trig function can I use to describe that situation right there? I'm going to label this x because that's going to be the x coordinate of that vertex on the left of where I've labeled x. So can't I say the sine of 36 degrees equals x over a? So my x-coordinate is going to be sine of 36 degrees times a. Well, sine of 36 degrees is just a number. So stick that in your calculator and see what number it is.
You said put sine of 36 in?
Mm-hmm.
Okay.
Make sure you're in degree mode.
Yeah.
Should be a little more than a half.
Yeah, 0.587. But what about the A?
It's 0.587a. That's what x is equal to. Which gives me my left coordinate. 0.587a is the x coordinate. Negative. Right? Got to be negative. We can see on the graph that it's negative. And likewise, to get the y-coordinate, what equation can I write? A trig equation. There's the y-coordinate.
So that would be sine.
We're trying to relate y with a and 36 degrees.
Okay, so cosine.
So y is equal to cosine of 36 degrees times a. What's cosine of 36 degrees?
0.809.
Here's the coordinates of that vertex. Minus 0.587a is the x-coordinate, minus 0.809a is the y-coordinate. Do the same basic thing over here, although I can certainly see by symmetry that this is just going to be the positive x-coordinate, and the y-coordinate's the same. Now, addressing the problem of none of the other vertexes are going to be on an axis, I don't know how that can be. Because that's definitely a regular pentagon, and I can divide it up into 5 triangles, and each triangle is congruent with one another. The bottom 2 vertices are certainly not on an axis, but I got to think that one and that one are.
Well, that would mean that the top 2 triangles there share a right, they both have a right angle.
You're right. You're absolutely right. And that angle can only be 72 degrees.
Yeah.
In other words, the way to do this is to, our answers, hold on, let's see. If this is one vertex, then, hold on, let's relook at this. I know that I can create this thing by drawing a bunch of 72-degree angles. And that picture doesn't make sense because all 3 of these would have to total 180. Okay, let's start this picture again here. Okay, we got one vertex there at a comma 0 and a 72-degree angle where this side is also A. So there's one triangle. And now, if I want another 72-degree angle, I got to take it out to like there. So that would be 72 degrees. That's 72 degrees. And a third one gives me what? 216. Well, 216 is about to there. So there's another vertex where that's 72. And the rest I'm going to split in half. He's right. None of the other vertexes are on the, but each of these angles is 72. In other words, we're still going to be able to answer the problem with the same strategy. Right? We're going to solve this triangle for that coordinate. In other words, if I drop a dotted line from that next vertex, I can solve for the x and the y coordinate in the same way that I did in the incorrectly drawn picture. Right? So let's figure out this coordinate here. And then probably we should go on to the next one, because otherwise we're going to spend the whole time here. So,
wouldn't it be easier to find the coordinates in polar and then convert to rectangular? Because that would just be like A72, right?
Yeah.
72 degrees to the next.
I hadn't thought of doing it that way. I'm not sure that's easier. Let's try it that way.
Okay.
Convert to polar. Problem is we don't have this defined as a rectangular function. So converting it to polar, I could certainly define this line as
I mean, if it's a rectangle, if it's a regular pentagon, then
I think it's easier to do this way, although I'm a little bit surprised that this is in your polar section. In other words, we can solve this using trig.
oh, okay.
And that's the way I can see to do it. I'm not sure I can see how to do it using polar. In other words, we need the x and y coordinate on this point. Well, the x coordinate, what do I know? I know that the cosine of 72 degrees equals x over a. So x is a times the cosine of 72. That's the x coordinate. And the y coordinate is a sine of 72. So that's how we're going to get that coordinate. What's cosine of 72? .309a is the x coordinate of that thing. What's the y coordinate? What's the sine of 72? There's your coordinates of that vertex.
Okay.
Now, how are we going to get the coordinates of this one?
Would we do 180 minus?
Well, hold on. Let's see. We need this angle right here, don't we?
Yeah.
What is that angle?
The 72 times 2. So
144
okay.
minus 90.
Oh yeah.
So that angle is 54 degrees. Now you use your same trig functions. So this point is going to be, it's a negative x coordinate, we can see for sure. It's going to be the cosine of 54 degrees times a. That's the x coordinate. The y coordinate is going to be positive sine of 54 degrees times a. This coordinate down here, we need this angle. What's that angle? Add up the 372s and subtract 180 from that. See why you have to do that?
Oh, okay, yeah. So 36.
Well, it's 216 minus 180, yeah, that's 36. So once we have those angles figured out, then we can always figure out this coordinate just using trig.
Okay.
And then we're going to do the same thing down here. So this actually is a fairly difficult problem because each of these angles is different. In other words, that one's 72 degrees. This one was 54 degrees, and so forth, when we go to solve these right triangles that we end up creating. Now again, there might be a way to do this with polar. That is R. Can't see how to do it though. I don't know. There might be a way to do it by converting everything to polar first. Might be easier that way. You can see that doing everything in rectilinear, each one of these triangles I had to use basically the trig equation that R is equal to x cosine, or x is equal to R cosine of theta. Or A equals x cosine of theta. When you use polar, you do the same exact thing that I just did. In other words, to figure out the dimensions of this point right here, I realize I'm looking at the cosine of 72 degrees equals, or rather, A equals, no, I mean, I can see when I did it rectilinear, I used the same relationship for these triangles that you use when you convert polar to rectilinear or back the other way. So in a way I used polar, but it really was just all trig. I'm not real sure how to use polar to do this in a different manner. It might end up being the same thing. It might end up just being, there's nothing really different about using polar.
Okay.
I don't think, but I'm not sure. There may be some technique that you can do this a little faster than by using trig. Huh. Interesting. Yeah. The key to graphing it is knowing that central angle is 72 degrees. That keeps you from putting the vertices on the axes like I was trying to do. All right. You got another one?
No, actually that's my last problem.
Okay. Any questions about polar? There's one last thing let's talk about. Okay. Let's see. I can find what yeah. I only laid out 3 equations. There's actually a 4th one. Theta is the inverse tan of y over x. And I think you can see that. That's only if x is greater than 0. It's equal to the inverse tan of y over x plus pi if x is less than 0. And your book may not spell it out quite like this. There's lots of ways to make this a lot more complicated. But this is the easiest way. Okay. In other words, if I have a point that is 2, 2, then theta is the inverse tan of 2 over 2. X is positive, so it's just the inverse tan of 1. That's 45 degrees. Okay? Let's make x negative. So that the coordinates are now negative 2, 2. Well, what is theta? Well, now x is negative, so it's this one down here. It's not whether that quotient is negative, it's just x. We don't care what y is. If x is negative, we're going to need to take the inverse tan of negative 1, which is what? It's negative 45 degrees. Plus pi gives us our 135 degree angle. Okay? So that's what these bottom two things mean. Is when you're trying to solve for theta, if you have an xy coordinate, and this is a very typical problem in polar coordinates, is where they give you an xy coordinate and they want you to come up with the angle, theta. In other words, what's the polar definition of this thing? Well, I could figure out the length of that, but the key to figuring out how to express this point in polar coordinates is coming up with theta. And theta depends on these two. Memorize both of those. Okay. And remember, it's not if this quantity is positive or this quantity, it's just the denominator. What if x is equal to 0? What's theta?
Infinity.
No? This is the one time in math where you can divide by 0 is when you're taking the inverse trig function of it. Where is the tangent undefined? 90 degrees or minus 90 degrees. So if x is 0, theta is either plus 90 or minus 90, depending on what y is. In other words, this is a real problem. Theta equals the inverse tan of 2 divided by 0. That is not undefined. That's pi over 2. If theta equals the inverse tan of minus 2 over 0, that's minus pi over 2, which are the two places where tangent is undefined. Well, this thing is undefined, so I'm looking for the angle that gives me that undefined. And that angle is pi over 2, 90 degrees or minus 90 degrees. If you look at the tangent curve, you have asymptotes, minus pi over 2 and pi over 2. And at both of those places, tangent is undefined. So inverse tangent of undefined is pi over 2 or minus pi over 2. But the undefined is division by 0. I always thought that was rather interesting because this is the first time in math where you're allowed to divide by 0. And it's only when you're taking inverse tan, inverse secant, inverse cosecant, inverse cotan would all have an angle associated with where they were undefined. In other words, division by 0 going on in the argument. But that's straight out of my book, these two equations. Your book I've seen other books that don't define it this way. They define it in a way that's far more complicated. To me, this is the easiest way to define it. How you come up with theta, if you know what x and y are. All right. Good to go?
Yeah.
Okay. I will talk to you next Tuesday night.